welcome to Study Heroes. In this video we'll be going through the 2021 November paper, the Physical Science Paper 2 paper, and we'll be looking at question 7 that should cover acids and bases. Let's get into it. In 7.1 they ask, or they state, sulfuric acid H2SO4 ionizes into two steps as follows. Step 1, H2SO4 plus H2O produces HSO4 minus plus H3O plus, and then they give us the K value for both reactions. So in reaction 2 we have HSO4 minus plus H2O, which produces SO42 minus plus H3O plus. 7.1.1 states define an acid in terms of the Lorentz-Bronsted theory. So according to the Lorentz-Bronsted theory, an acid is a proton donor. It donates an H plus ion. I'm going to leave this here in case they ask what a base is according to the Lorentz-Bronsted theory. And a base is just a proton acceptor. Also, if they ask us the definitions of an acid and a base according to Arrhenius theory, we'll know that an acid, according to Arrhenius theory, is a substance that produces hydrogen ions or hydronium ions when it dissolves in water. And a base is a substance that produces hydroxide ions, OH minus ions, when it dissolves in water. So for 7.1.1, an acid is a proton donor according to Lorentz-Bronsted theory. In 7.1.2, they ask, write down the name or formula of a substance that acts as an ampholyte in the above equations. Give a reason for the answer. I'd like to start off by going through what a definition of an ampholyte is. An ampholyte is a substance that can act as either an acid or a base. So it has dual properties. It can donate a hydrogen atom or accept a hydrogen atom according to Lorentz-Bronsted. So let's go back to these two reactions. And we can see here in reaction 2 that we start off with HSO4 minus, and it donates a hydrogen ion to form SO42 minus. And if we look here, we have HSO4 minus again, that is formed from H2SO4 losing one hydrogen ion to form HSO4 minus. Both of these are hydrogen donated reactions, so these here are acids. And because it formed this is the conjugate of this substance, and therefore this is a base. So in reaction 1, HSO4 minus is a base because it's a conjugate of the acid, but in reaction 2, HSO4 minus is an acid because it's a proton donor. So when they ask you to identify the ampholyte, you have to see which substance is used twice. In this case, it's HSO4 minus. That will be a good indication that this is most probably our ampholyte. And in one case, it needs to act as a base, and in another case, it needs to act as an acid, and that's how you've identified it as an ampholyte. So going back to 7.1.2, that means our answer is HSO4 minus and the reason is it because it acts as a base in reaction 1 and an acid in reaction 2. In 7.1.3, they state that the conductivity of the solution of HSO4 minus and H2SO4 aqueous are compared. Which solution will have a lower conductivity? Explain the answer. Now, conductivity is the flow of electrons. So what we need is a solution that has a mixture of ions so that the electrons can flow. So if we look here, we have two reactions that form ions. That's usually the case of acids and bases. And we've been given K values. Now, what are K values? K values just represent the concentration of products over the concentration of reactants. So, if we have a high concentration of reactants over products, our K value will be between 0 and 1, so it will be less than 1. And if we have a high concentration of products over reactants, we'll have a really high K value, greater than 1. In the first case, this means that our yield is low, and in the second case, our yield is high. And because our reactions produce ions, that means that a high yield will produce lots of ions and therefore have a high conductivity. So this second case will have a high conductivity. Whereas for a reaction that produces ions, if the K value is low, then we'll have a low conductivity. So, if we go back to our question, they want to know which solution will have a lower conductivity than the rest. So we look at our K values once again. We see that this is a very low value. It's less than 1. And this is a very high value. That's greater than 1. Therefore, the low value one will produce a low conductivity, and therefore reaction 2 produces a low conductivity. So our answer to 7.1.3 is HSO4 minus. The reason will be it produces a low conductivity because it has a low K value. In 7.2, they state that the pH of a hydrochloric acid, HCl, is 1.02 at 25 degrees Celsius. And then they ask us to calculate the concentration of the hydrochloric acid in 7.2.1. So 7.2.1, we've been given the pH of the hydrochloric acid solution at 1.02, and they want us to calculate the concentration, I'll indicate that with brackets, of hydrochloric acid. Now, because they gave us the pH, we can work backwards to find hydromium. If we look at the back of our exam paper on our formula sheet, we'll find this formula here. We can use this formula to get the concentration of hydromium. So we'll have this formula, pH minus log H3O plus. Step 1, to get the concentration of hydromium, we've got to multiply both sides by -1. We'll get that. After that, we got to raise negative pH and log H3O plus by 10 to get rid of the log. So we'll have this 10 minus pH. If we raise it to the 10, we get rid of the log and we are left with H3O plus, so we'll end up with H3O plus. And therefore, the concentration of H3O plus will be equal to 10 to the power negative 1,02. If we punch that into our calculator, we'll get 0,0955. That's the concentration of hydromium. So if we had a balanced equation, would have hydrochloric acid dissolved in water, forming Cl minus plus H3O plus. Like we'll always have our hydromium compound, and therefore this hydrogen atom from our hydrochloric acid gets donated to H2O to form that hydromium, and therefore we are left with Cl minus. And this equation is balanced. We have a 1-to-1 relationship with hydrochloric acid, and therefore the concentration of the hydrochloric acid is also 0,0955. Normally we would be given the volume of the hydrochloric acid, but we haven't been given that in this case, and therefore it's okay to just assume there's a 1-to-1 relationship in terms of concentration because not enough information was provided. So we'll have 0,955 moles per decimeter cube. In the next question, they gave us additional information. They say this hydrochloric acid reacts with sodium carbonate, Na2CO3, according to the following balanced equation. So we've been given this equation, it's balanced. 50 cubic centimeters of the HCl solution is added to 25 cubic centimeters of 0,75 moles per decimeter cubed of sodium carbonate solution. And then 7.2.2, they ask us to calculate the concentration of the excess hydrochloric acid in the new solution. So as you can see, they put excess in capital letters. That's very important. If they do so, anything bold, anything capitalized needs to be paid attention to. So what does excess mean? Excess means that there's more than enough, which lets us know that hydrochloric acid is not the limiting factor in this reaction. So from this 50 cubic centimeters of hydrochloric acid that was added to the sodium carbonate, not all of it will be used. Some of it will be left behind, and that's called the excess. So what do they want us to calculate in 7.2.2? The excess hydrochloric acid concentration in excess. How do we get it? Well, we need to know the total hydrochloric acid and it will be a product of the used hydrochloric acid plus the excess. I'll just put an E for excess hydrochloric acid. Now the concentration of the total hydrochloric acid used was calculated in the previous question, and we got 0.0955 moles per decimeter cube. That means if we can calculate the concentration of the used hydrochloric acid, we'll be able to find that concentration of the excess hydrochloric acid. So how do we calculate this? Let's see what else they gave us. Seems like we'll be using sodium carbonate. They gave us a volume and a concentration of the sodium carbonate. So if we go to the formula for concentration, we'll see that it equals number of moles over volume. They gave us concentration, they gave us volume, which means we can get the number of moles of sodium carbonate. After we get the number of moles of sodium carbonate, we can use this balance equation to get the number of moles of hydrochloric acid. And then once we have the number of moles of hydrochloric acid, we can get the concentration of that hydrochloric acid that's being used to react with the sodium carbonate. So let's do that. For sodium carbonate, let's just write down what they gave us. They gave us volume at 25 cubic centimeters, and they gave us concentration at 0.075 moles per decimeter cube. So now we can get the number of moles, making the moles the subject of the formula. We get N equals CV, so multiply V on both sides. We get N equals CV. Substitute the values, we get 0.075 multiplied by 25. But we have here cubic centimeters. We need to make sure this is in decimeters so it can cancel out with this decimeters and give us moles. And to convert cubic centimeters to decimeters, we have to divide by 1,000. So if we punch that into the calculator, 1,875 times 10 to -3 moles. Remember, this is for sodium carbonate. In order to get the moles for hydrochloric acid, we have to go back to the balanced equation. When we see that we need 2 moles for every 1 mole of sodium carbonate, 2 moles of hydrochloric acid for every 1 mole of sodium carbonate solution. Therefore, the number of moles for the hydrochloric solution is going to be twice that of the number of moles of the sodium carbonate. Therefore, it will be 2 times that value there, 875 times 10 to the -3 moles. So if we punch that into our calculators, we get 3,75 times 10 and -3 moles of hydrochloric solution. So now we can go back to the formula for concentration. Since we now know the number of moles and we know the volume of the solution, which was 50 cubic centimeters, just to let you know, it was stated here, 50 cubic centimeters of the hydrochloric solution. Therefore, we'll have a concentration of 3,75 times 10 -3 over 50 divide by 1,000 for one to leave it in decimeters. If we punch that into our calculators, we get 0,075 moles per decimeter cubed. Remember, we're not finished. We're trying to get the concentration of the excess. So if we make the excess concentration the subject of the formula, we take the used to the other side of the equation, or we subtract both sides by concentration of the used hydrochloric solution, and we'll get HCl in excess equal into the concentration of the total hydrochloric acid minus the concentration of the used. So the total was 0,0955. The used, we just calculated as 0,075, which means the excess concentration is 0,0205 moles per decimeter cubed. And that's our final answer. So that concludes question 7 of the 2021 paper. I hope it made sense. Please do like, share, and subscribe so that you could help the channel, and look forward to more videos. Bye.